In mathematics, the Golomb sequence is a non-decreasing integer sequence where the nth term is equal to the number of times n appears in the sequence. The first few values are 1, 2, 2, 3, 3, 4, 4, 4, 5, 5, 5. Explanation of the terms. Third term is 2. Note that 3 appears 2 times. Second term is 2. 2 appears 2 times. Fourth term is 3, and 4 appears 3 times. The following function uses recursion to calculate the nth number. Here we have an arrow function called Golomb. We take in an n parameter, and we say our base case. If n is equal to 1, we return 1. Else we return 1 plus Golomb n minus Golomb n minus 1. Extremely confusing, but when you console log it and you put in 9 at the end part, when you put in 9 as an argument, you should get 5. But because of that, even though the answer is correct, it will be extremely slow, and we'll also be making a lot of recursive calls, adding to the call stack. The time complexity would be O2 to the nth power. This can be solved through dynamic programming with memoization in hash tables. Comment this out. Here we have Golomb 2, a second function where we pass in a memoization object to keep track of the values that are computed and decrease the amount of recursive calls being made. Here we have our base case again. If n equals 1, we return 1. And then here is the part that's different that's going to change things. If the memoization object at n has a value, we'll return the value of memoization n. If it doesn't, here we add the value of memoization n. Here's the console log to see a better visual of what's going on. Again, it should return 5. Here we have 5, but what's more important is the objects that's being console that's being logged. So we know 2 is 2. We also know 3 is 2. We know 4 is 3. We know 5 is 3. And each time we get a new number, we're adding it to the memo object. This way we can just check the memo object instead of having to make so many recursive calls, even though we're calling the function multiple times. Here we go. Here's a cleaner version with no comments. So again, you see we're stating out if the n equals 1, we'll return 1, which is the base case. Then we check the memoization object to see if it's there, and if it's there, we just return it. And if it's not, we just add it to the memoization object so that we don't have to call the function again, decreasing the amount of recursive calls that we make. A more important part of data structures and algorithms that I don't really think is talked about is when to use these things. Like, we can use memoization n, but we can also just create a bottom-up solution that does it. Or we don't even have to use recursion at all. We can just do a regular for loop that'll handle this for us. But in situations like in the legendary power surge data structure that we made last week, here we just use a simple equation to solve everything. So it's not really as complex as needed as it could be. So it's simpler to use recursion here to make a more elegant, smaller solution.